Okay, let's finish the last part of number 22. Okay, so I just went ahead and I wrote down some information from, again, the previous video. Here's our lambda, lambda sub 3, which is equal to 3, and we're trying to find the associated eigenvector. After substituting this lambda back into our characteristic equation, right? We just substitute our numerical value lambda, and then we obtain, I probably should have used green because I think that's what I used last time, right? And then these guys change, right? The diagonals. And then you use our REF function on your calculator, and then it gives you this guy, which you notice is very similar to the other matrices, but the only difference is you have a -1 here. But let's go ahead and look at the relationship. It's actually not too bad. Okay, so what do we have? Well, it looks like A minus C equals 0, and it looks like B plus C is equal to 0. And then, of course, that just says 0 equals 0, which is a true statement, so it's we don't have to deal with that part. And here, let's see, we can definitely solve for A in terms of C. So A is equal to C, and similarly, B is equal to -C. Okay, so this is really nice because now you just have to choose a value for C, and then, I mean, once you choose a C, then you know what A and B is because it's really just, it's right here. So let's see, let's call it, so V3, and if C is, I don't know, let's just say C is 1. Okay, if C is 1, okay, then that means A is 1 because A equals C, so 1, and then B is just the opposite of C, so that's -1. And if you want to write it again in terms of the transpose, 1, -1, 1, so the transpose of this row vector is, right, this column vector. And again, you can choose any value. I don't know, if C is 32, I don't know, 320, then, well, A is equal to C, so A is also 320, and then this guy is just the opposite. But again, I mean, why choose 320 when you can choose 1? And again, these are non-zero vectors, so we don't want to choose 0 here. So we found all our eigenvalues and our associated eigenvectors. And so the goal of the problem was to find the general solution. And so by the theorem in the book, we know that the general solution, so let's go ahead and write it as x of t, right, bold x of t. And we have our n is 3, right? So it's really up to C3. The book talks about Cn. N linearly independent vectors, so we have 3 linearly independent vectors. And so I'm just going to go ahead and write it as from the book, C1 times x1 of t plus C2 x2 of t plus C3 x3 of t. And then we know what this guy, and this guy are, right? They're just our x1, x sub 1 of t is equal to our eigenvector, right? V1. Let's use some colors here. So there's my pink. And so we have V1 e to the lambda 1t plus C2 V2 e to the lambda 2t plus C3, let me get a pink here, V3 e to the lambda 3 times t. And so we obtained the following. So C1, okay, so let me just insert the vectors here. So my first lambda was 1, so e to the 1t, so that's just e to the t, plus C2, I'll go ahead, again, insert the vectors in a bit. Lambda 2, what was lambda 2? Was it positive 2 or negative 2? I think it was negative 2, yes, negative 2, so e to the negative 2t, plus C3, and then our eigenvector e to the, and I think that was positive 3, so 3t. Okay, so let's insert our eigenvectors. So I know this guy was, oh, whoops, I didn't want to do that. Let's see, did I use a blue? I don't know if I used blue or not, but okay, so our eigenvectors are 1, what was it was 1, negative 1, 0. This is a little bit bigger. Well, we just found our C3, might as well put that in, 1, negative 1, 1, and then the other eigenvector, my V2, was 0, 1, negative 1. Okay, so now it's just some scalar, we have scalar multiplication here, right? Let's distribute that C1 in there, and then of course this is a non-scalar, but we can still multiply it in. We can rewrite this as C1 e to the t, negative C1 e to the t, and then we just have 0, plus, this is nice, 0 C2 e to the negative 2t, it's a negative, negative C2 e to the negative 2t, plus C3 e to the 3t, negative C3 e to the 3t, and we know a is equal to c, so you can just rewrite that. And then, of course, vector, these are all column vectors. We can add them using matrix operations. So if we add the rows, we get, right, I'm adding this row first. C1 e to the t plus C3 e to the 3t, negative C1 e to the t plus C2 e to the negative 2t minus C3 e to the 3t, and then finally negative C2 e to the negative 2t plus C3e to the 3t. So this is a, right, this is a 3 by 1 matrix, right? We have we have 3 rows, right? And then this is all one column because we're really adding these guys to make one entry. And that is your, your general solution, right? This guy is really, well, let's actually go ahead and write it out. X1 of t, right, is equal to C1 e to the t plus C3 e to the 3t. X2 of t is negative C1 e to the t plus C2 e to the negative 2t minus C3 e to the 3t, and X3 of t is the last one. And if you notice in the back of the book, they don't have this exact answer, and that's because they chose, so my eigenvalues, the order that I put them in was, I think lambda 1 was 1, lambda 2 was negative 2, and lambda 3 was, was that positive 3. And they said, I just like the 1, 2, 3 because of the subscripts. It matches nicely. But they said, lambda 1 is going to be negative 2, lambda 2 is 1, and lambda 3 is 3. So, they just wanted, I guess, to put the negative first and then work with the positives. But they're, either way, again, the order doesn't matter. You still have the same general solution. And there's no initial condition, so this is your final answer. And finally, the end of number 22.